So let's talk about solar energy. It feels like it went from this kind of niche, futuristic tech to an absolute global superpower almost overnight. It's moving at a breathtaking speed. Today we're going to break down how it all works, starting from a single particle of light all the way up to these massive, sprawling solar farms that are literally changing how we power the world. Let's dive in. Just to give you a sense of the insane scale we're talking about, look at this number. In 2023 alone, China installed 2.5 times more solar power than they did the year before. I mean, that's not a 2.5% increase. That's a 250% jump. In a single year, the solar boom isn't coming, people. It's already here. And honestly, it's moving way faster than pretty much anyone expected.
And here's what that looks like on a global scale. Back in 2004, the entire world had just 1 gigawatt of solar capacity. It's kind of funny to even think about now. By 2022, we were adding 250 gigawatts every single year. And if you look ahead, the forecasts are just staggering. We're talking about hitting nearly 8.8 terawatts by 2030. What you're looking at right here, this isn't just growth. This is an energy revolution playing out in real time.
Okay, so that's the big picture, the massive scale. But how does it actually work? How does a simple ray of sunshine hit a panel and end up charging your phone? To get that, we need to zoom in. Way in. We got to look at the incredible science that makes it all possible.
The secret sauce, the magic trick, it's all thanks to this beautiful piece of physics called the photovoltaic effect. Now, I know it sounds super complex, right? But it's actually this incredibly elegant process that's happening inside every single solar cell, billions of times a second, all across the planet.
And the star of this whole show is silicon. Yep, the same stuff that's in computer chips. It's also the heart and soul of pretty much every solar panel. It's what's known as a semiconductor. That just means it's not a great conductor, like copper, but it's not an insulator, like rubber either. It's somewhere in the middle. And that in-between property is its magic, because it means we can control exactly how it handles electricity.
And here's how we control it. Scientists do this thing called doping, where they add tiny amounts of impurities to the silicon. Think of it like baking a cake with a secret ingredient. They create 2 different layers. One layer, the N-type, gets atoms that have extra electrons, giving it a negative charge. The other layer, the P-type, gets atoms that are missing electrons, which creates these little positively charged holes. So you've got this perfect imbalance. One side has too many electrons, and the other side desperately wants them.
So here's where it all comes together. First, a particle of light from the sun, that's a photon, slams into the silicon and knocks one of those electrons loose. Now, because of that imbalance we just talked about, that free electron immediately wants to jump from the negative side to go fill one of those empty holes on the positive side. But the boundary between the 2 layers acts like a one-way gate. It forces all those moving electrons to travel along a circuit to get where they want to go. And guess what? A directed flow of electrons, well, that's what we call electricity. Simple as that.
Okay, so that's the core science. But out here in the real world, this technology comes in a few different flavors. Each one has its own pros, its own cons, and is best for different kinds of jobs. It's kind of like a whole menu of solar options.
Let's break it down real quick. Monocrystalline panels, they're your high-performance option. Super efficient, which makes them perfect for your rooftop where space is limited. But they're also the most expensive. Then you've got polycrystalline panels, a little less efficient, but they're cheaper, which is why you see them covering huge fields in big solar farms. And then there's this cool stuff called thin film. It's flexible, it's lightweight, you can even build it right into windows or roofing materials. So the main takeaway here, there's no single best panel. The best tech is always the one that's right for the job.
So how do these huge utility-scale projects actually get funded and built? Well, it all comes down to the business model. And as you can see, more than half of them are driven by fixed prices set by governments, or tariffs. Another big chunk comes from competitive auctions, where companies bid to build a project for the lowest cost. But check out this growing slice, corporate power purchase agreements, or PPAs. That's when a huge company, think Google or Amazon, agrees to buy all the electricity from a new solar farm for the next, say, 20 years. That guarantee makes it way easier for a developer to get the loans to actually build the thing.
All right, so we've got this amazing, proven technology. We have the financial models to build it out at a massive scale. But it's not all sunshine and roses. The industry is facing some very real, very challenging growing pains.
Exactly. I mean, it seems too good to be true, right? We've basically cracked the code on making cheap and efficient solar panels. So what's the catch? What's stopping us from going even faster?
Well, the problems are no longer about the panel itself. They're about the entire system around it. The International Energy Agency points to a few major roadblocks. Probably the biggest one is our electrical grid. It's just old. There are literally projects waiting in line for years just to get permission to connect. Supply chains for key parts can get totally snarled. And then you've got this wild problem called curtailment. This is when, on a perfectly sunny and windy day, solar and wind farms produce so much cheap electricity that the grid can't handle it, and the operators are literally forced to shut them off and waste that clean power. Throw in slow government permitting and high interest rates, and you can see how these obstacles really start to stack up.
And this quote from a recent IEA report on Chile just sums up the problem perfectly. So, Chile has some of the best sunshine on planet Earth up in its northern deserts. But all the people, the big cities, the industries, they're hundreds of miles to the south, and they just don't have enough giant power lines to get that clean energy from where it's made to where it's needed. All that incredible solar potential is just stranded. It's a perfect case study of how the challenges shifted from making the power to moving the power. So keeping all of those challenges in mind, what's the path forward from here? Because believe me, the world has set some incredibly ambitious goals for itself.
At the big COP28 climate conference, governments from all over the world agreed on this massive goal: triple the planet's renewable energy capacity by the year 2030. That is a monumental task, and you could bet that solar power is expected to do most of the heavy lifting to get us there.
And that really brings us to the most important takeaway of all. The basic science, it's solved. The technology, it's mature, it's efficient, and it's cheaper than it has ever been. The real challenge, the thing standing between us and that 3x goal, isn't about inventing a better solar panel. No. It's about building bigger grids, streamlining permits, and fixing our supply chains so we can actually deploy the amazing tech we already have.
So we end with this question. We have figured out how to turn tiny specks of silicon into a genuine global superpower. The tools to power our world with the sun are right here, in our hands. The crucial question is no longer a scientific one. It's an implementation one. The tech is ready. The real question is, are we ready to build a system that can finally capture it?